Okay, we'll go ahead and get started here. Okay, those of you on Zoom, can you hear me okay?
Yes.
Yeah, I can hear you.
Okay, great, thanks. Okay, so we are going to continue on with reactions of alkenes and alkynes. I sent out an announcement. There is a sampling assignment on this subject. I'm going to okay, we got one person that's waiting to join. I'm going to go ahead and share my screen. Okay, so once again, these are some of the major reactions of alkenes. Okay, we've gone over the first three of these. We're going to cover the last two today, as well as some reactions of alkynes. I'm going to skip through this. Okay, so we talked about regioselective reactions, and these are ones in which a particular positional isomer is formed. Okay, for example, when we add HCl to propene, H goes to carbon number 1, Cl goes to carbon number 2, and not the other way around. Okay, this is according to Markovnikov's rule. The rich get richer when it comes to hydrogen. Markovnikov's rule applies to addition of other hydrogen halides like HI and HBr. It also applies to the acid-catalyzed addition of water. Okay, in 1-methylcyclohexene, carbon number 1, which is the one carrying the methyl group, has the fewer hydrogens. There's no hydrogens here, and there's one hydrogen. So the rich get richer, the other side gets the OH. So this is the only product and not this other isomer. All right, this is an explanation of why the addition of HCl and other hydrogen halides and water is regioselective. Okay, it's because the more stable carbocation is formed. Okay, so the first step involves formation of a bond between carbon and hydrogen. One of the pairs of electrons in this pi bond reaches out and attacks the hydrogen. This pair of electrons then shifts onto the chlorine, and we get a carbocation. Okay, we have an empty spot here on this carbon because we used up a pair of electrons to form this bond. Okay, the more substituents, the more alkyl groups or carbon groups that you have around a positively charged carbon, the more stable it is. The faster it's formed and the lower energy it is. Okay, this is the structure of a carbocation. It has a trigonal planar geometry. It has a vacant 2p orbital. And this is the order of stability. Okay, the more carbons you have bonded to that carbocation, the more stable it is. Okay, so it's primary. Primary is the least stable, well, after methyl, and then ethyl, which is an example of a primary, then isopropyl, an example of a secondary, and then tert-butyl, an example of a tertiary. Okay, the explanation here is There's actually two reasons. One is the inductive effect. Let me back up here. Okay, here's the inductive effect. These methyl groups are pushing electrons toward that electron deficient center. And the more alkyl groups or R groups you have, the better they are at stabilizing that electron deficient carbon. Okay, so anytime you can spread out a charge, that lowers the energy, that renders it more stable. I'm going to go through this again. Addition of water requires an acid catalyst. Okay, here's the step-by-step mechanism. Okay, the alkene takes a proton from hydronium. Okay, water is not nearly as acidic enough. So typically you would mix sulfuric acid in about 10 to 20%, and that would form hydronium ions. So this gets protonated with a hydronium ion, and it forms the more stable secondary carbocation. Right, the next step is water uses a pair of electrons to donate and form a new covalent bond. Okay, this is strongly acidic solution, so the concentration of hydroxide is extremely small. So it's water, not hydroxide, that's going to add. All right, and then we have taking a proton away. This is done in excess water. Okay, so this takes away a proton. We get our alcohol. And because hydronium is a catalyst, okay, by definition, you put a catalyst in at the beginning, you get it out at the end. All right, and okay, this is really the same thing, except we're using methanol instead of water. Same mechanism. We get an ether instead of an alcohol. We went through this last time. I won't spend additional time on that. Okay. This is probably about the point where we left off. Addition of halogens. Okay, we can add bromine or chlorine to a double bond. And all that's required here is to mix the two. The reaction occurs almost immediately. This can be done either with bromine liquid, or more commonly it's in a solvent such as methylene chloride, dichloromethane. Addition of bromine is a simple chemical test for a double bond. It's a simple chemical test for a double bond. Bromine has a dark red-brown color, and when it adds to a double bond, the dibromo compound is usually colorless. So you see an immediate decolorization, immediate disappearance of that red-brown color if there's a double bond present. This reaction is stereoselective. It's not regioselective, but it is stereoselective. If the double bond is part of a ring, you would only get the trans isomer. Okay, if the double bond is not part of a ring, you can't tell because the product would have free rotation. But this is why we only get the trans. Okay, first thing is the alkene attacks bromine. Bromine then attacks the positively charged carbon. We form this three-membered ring. Bromine has a plus charge since it has two bonds, and the bromide actually has to attack carbon from the backside, from below. Okay, and it can attack either from this side or this side. Okay, it has to attack the opposite side. Okay, and since it attacks the opposite side, we form a bond here. We break this bond, that becomes a lone pair. Okay, nothing happens to this bond, but the two bromines will end up anti to each other. And if the alkene is part of a cyclic structure, then the bromines will be trans. Okay, so it is stereoselective. You only get trans. Okay, so here's an example. We have the cycloalkene. When bromine adds, we only get the trans 1,2-dibromo. Okay, rearrangement. The two most common forms of rearrangement are an alkyl, usually a methyl shift, or a hydride shift. Okay, and that helps to explain why we don't get this expected product. Instead, we get mostly this one. Okay, so it starts out just like we would expect. Double bond picks up an H, rich get richer, carbon number 2 gets the plus charge. The minor product comes about when chloride then attacks carbon number 2, but then the major product occurs when we have a methyl shift. Methyl pulls out its electron pair, moves it over to carbon number 2, and what that accomplishes is we go from a secondary to a tertiary. Okay, so that makes it more stable, it lowers the energy. And then chloride attacks, and when we're drawing a mechanism, we always go negative to positive. Okay, so opposite charges attract, so this step occurs very quickly. Here's an example of a hydride shift. Okay, and I don't believe we did these examples. Okay, notice here, this is a rearrangement by ring expansion. Okay, let's take a look at the first one. Okay, the name of this would be vinyl cyclobutane. This is a vinyl group. And we are adding HBr to that. Our alkene picks up an H, gives away both of its electron pairs to the bromine. We have two H's here. So this becomes a CH3, rich get richer. And then what happens here is that the ring will then open and close. Okay, so we'll have a ring open and close. Okay, so this pair of electrons gets removed from this carbon, it moves over to this carbon. That gives us a 5-membered ring. Okay, and there's two driving forces for this arrangement. The first one would be we're going from a secondary to a tertiary. Can you think of what another driving force might be that would make this intermediate more favorable? Okay, how about bond angle strain? Okay, we've got less bond angle strain in a 5-membered ring than in a 4-membered ring. All right, and then bromide. Okay, the electrons move toward bromine, so it has a negative charge. And opposite charges would attract. This would come in and form the product. Okay, the second one is another example of a ring expansion. Oops, went the wrong way. Okay, so in summary, the carbon bearing a positive charge is sp2 hybridized, meaning it's trigonal planar, with bond angles of 120 degrees about it. The order of carbocation stability is tertiary, secondary, and primary. Carbocations are stabilized by electron withdrawing inductive effect of the positively charged carbon. Okay, so groups that donate electrons toward it will stabilize it. Methyl and primary carbocations are so unstable that they are never formed in solution. Carbocations may undergo rearrangement by a 1-2 shift when the rearranged carbocation is more stable than the original carbocation. The most commonly observed pattern of rearrangement is from a secondary to a tertiary. You also can observe primary to tertiary or primary to secondary, but most commonly it's secondary to tertiary. Carbocation intermediates undergo 3 types of reactions: rearrangement by a 1-2 shift to a more stable carbocation, addition of a nucleophile to form a new covalent bond, okay, such as a halide ion or a water molecule, or loss of a proton to give an alkene. Okay, that is the reverse of the first step in addition of HX, or the acid catalyzed hydration of an alkene. Okay, next we're going to introduce another reaction, a different reaction. This is called hydroboration oxidation. Okay, this involves 2 steps. Okay, the reason that you'll see this convention if these are numbered, say 1 and then 2 over the arrow. Okay, that indicates that this is 2 steps. Okay, you wait till the first step is finished before you begin the second step. Okay, so this is a shorthand. If the numbers were not here, okay, if we omitted the 1 and 2, that tells us we just mix everything together all at once. Okay, so we do the hydroboration first, and then we do the oxidation with hydrogen peroxide and hydroxide. Okay, and notice here that by Markovnikov's rule, we would expect H to go to carbon number 1 and OH to go to carbon number 2. But we get a product which is contrary to Markovnikov's rule. Okay, the pore get richer. Okay, so this is also regioselective, but it has the opposite regioselectivity of acid catalyzed hydration. Okay, this is why a mechanism is important. Okay, rather than simply memorizing, if we understand why this is the case, that helps us to explain. Okay. So we start off with our alkene. and we add borane, BH3, to that. Borane is so reactive that it either dimerizes to form diborane, or it complexes with some other molecule. In the older literature, okay, they would react an alkene directly with diborane. Okay, a couple of problems here is that diborane's a gas, so it's difficult to measure out exactly how much we need. And the other problem is that if diborane comes in contact with the air, it ignites. Okay, but if we stabilize borane with tetrahydrofuran, we form this complex called borane THF. What is the functional group in tetrahydrofuran? We got carbon, oxygen, carbon. What is that? Okay, someone on Zoom, speak up. What's the functional group? Oh, it's an ether. Okay. So this is a liquid, and so you have this in solvent, and when you can purchase this commercially with a known molarity, so you can measure out exactly how much you need. Okay, so borane does not have a lone pair on the boron, and it is sp2 hybridized, it's trigonoplanar. And because of that, okay, there's two things going on. One is boron does not have an octet. So it's a really good electron pair acceptor. Okay, the other thing is that hydrogen actually is more electronegative than boron. Okay, so this reaction is not only regioselective, but it is stereoselective. The boron and the hydrogen are added to the same side, cis or syn to each other. So unlike something like HCl or hydronium, where hydrogen has a partial positive charge, here, notice hydrogen has a partial negative charge. And so the alkene attacks the boron, not the hydrogen. Hydrogen then is nucleophilic or electron donating. So it forms this square intermediate. The second step, okay, which we didn't go through the mechanism for. Let's go back here. Okay, you don't isolate the borane addition product. Instead, once this reaction is finished, then we use hydrogen peroxide and sodium hydroxide to produce an anti-Markovnikov alcohol. Okay, let's look at reduction. Reduction of organic compounds typically involves addition of hydrogen content. And this particular reaction is called catalytic hydrogenation. We're adding 2 hydrogens. Okay, 1 to each side of the alkene, and our product then has no double bond. Okay, the addition of hydrogen to an alkene actually has a prohibitive activation energy. It doesn't take place at a reasonable rate at room temperature. However, if you add palladium, okay, palladium is element number 46 in the periodic table. It's a metal. Okay, if we add palladium, then we can carry this out at 25 degrees Celsius, room temperature, and 3 atmospheres. Okay, so this can be used with ordinary lab equipment generally, room temperature, a little bit above atmospheric pressure. You need thick-walled containers. But what is the palladium? What's its role, you think? It is a catalyst. Very good. Okay, so it significantly speeds up this reaction. Okay, this is not regioselective, but it is stereoselective. Okay, here is another catalyst that's commonly used as platinum. Platinum is actually in the same family. It's right below palladium in the periodic table. Okay, notice here that we get mostly the cis. Okay, so both hydrogens are added to the same side of the ring, of the same side of the double bond. So mostly cis, but not exclusively. Okay, so this is how the reaction takes place. Okay, both hydrogen and the alkene are absorbed on the surface of the catalyst. Okay, what the catalyst facilitates is breaking the bond between the two hydrogens. Okay, so going from A to B, okay, this bond is broken, and then a bond is formed between the alkene and the hydrogen. And then this hydrogen molecule does the same thing. We break the bond and then we add to this side. Okay, so the reason we mostly get syn addition is that because of the alkene being bound here. Okay, once in a while the alkene is released and then it rolls over and then hydrogen is added to the other side, which would give us the trans. But usually that doesn't happen, but once in a while it does. Okay, when we talk about this alkene is more stable than that alkene, when we talk about elimination reactions later on in the course, where we form alkenes, okay, the more stable alkene is preferred. Again, one of the ways that we can judge that an alkene is more or less stable is by calorimetry. Okay, we can perform this reaction. In the presence of a catalyst, we add hydrogen to an alkene, and then this is exothermic. And so using a calorimeter, we measure the heat that is released. It is exothermic because the two new sigma bonds are stronger than the pi bond that we broke. Okay, so it is, so heat is released. Okay, and you can see that ethylene is the reference compound here, and it has a delta H of negative 137 kJs per mole. Okay, if we replace one of those hydrogens with a methyl, okay, the heat of hydrogenation went down. So that tells us that propene is more stable than ethylene. Okay, an ethyl has almost the same effect as a methyl, so 1-butene, that's about the same as propene. However, when the double bond is internal, as in cis-2-butene or trans-2-butene, we can see that the heat of hydrogenation continues to go down. And by calorimetry, we can show that the trans is more stable than the cis. Okay, and that's probably what we would expect. Okay, if we take trans 2-butene and we replace one of these hydrogens with a methyl, we can see that the heat of hydrogenation continues to go down. And then if we replace all 4 of the hydrogens with methyls, okay, now it's down to negative 111. So the more substituents you have connected to that double bond, the more stable it is. Okay, so reduction involves net conversion of a weaker pi bond to a stronger sigma bond. The greater the degree of substitution of a double bond, the lower its heat of hydrogenation. The greater the degree of substitution, the more stable the double bond is. The heat of hydrogenation of a trans alkene is lower than that of a cis alkene, so therefore the trans is more stable. And the difference between cis and trans is due to non-bonded interaction strain in the cis alkene. Okay, so let me go back here. So what they're talking about there, this is the cis. Okay, so there's some repulsion occurring between these 2 methyl groups. Okay, it's like the torsional strain that we saw in the eclipse form of butane or in small cyclic alkanes. Okay, so heats of hydrogenation for cis-2-butene and trans-2-butene. In terms of that, the trans-2-butene is more stable than the cis by 4.2 kJs per mole. Okay, as we saw in chapter 4, one of the major differences between the chemistry of alkanes, alkenes, and alkynes is that terminal alkynes are weak acids. Okay, so here are some pKa values. Okay, we have water's 15.7. While we cannot remove this terminal hydrogen from an alkyne with hydroxide, we can with the conjugate base of ammonia, NH2. Okay, so there's a very significant difference in acidity among the alkynes, alkenes, and alkanes. Okay, so this doesn't work. This is a repeat of what we saw in the previous chapter. This doesn't work because we're trying to form a stronger acid, namely water, from a weaker acid, namely the terminal alkyne. But we can use the conjugate base of ammonia, which is called sodium amide. Okay, that works because ammonia is now a weaker base than a weaker acid, sorry, than the alkyne. Okay, we're going to come back. We're going to see this again in a later chapter, but this is where this acid-base reaction is useful. Okay, once we form, this is called an acetylide ion. Once we form this, we can react it with a haloalkane, okay, such as chloromethane, and we form a longer carbon chain. Okay, this is called alkylation, and it allows us to extend the carbon chain. Okay, and if we start with acetylene, we can actually extend the carbon chain both ways, both directions, with different groups. Okay, here we're extending it by 2 by using bromoethane. Here we are extending it by 3 on the other side by using 1-bromopropane. Okay, this is an important point. Okay, and we'll talk about this more fully in Chapter 7, but this type of alkylation is successful only for methyl and primary alkyl halides. Okay, so these are both primary alkyl halides. The halogen is bonded to a carbon which is directly bonded to only one other carbon. Okay, so something like let me draw that a little bit bigger. Okay, something like this would not work. Okay, this is what we call a secondary alkyl halide. This carbon is directly bonded to 2 other carbons. Okay, on the other hand, we could do it with this one because this is now a primary. Okay, just like with alkenes, we can also reduce alkynes to alkanes. Okay, if we start with an alkyne, such as 2-butyne, using a nickel, palladium, or platinum catalyst, and if you look at the periodic table, all 3 of these metals are in the same column. This can be done at about 3 atmospheres, room temperature. We add 2 moles of hydrogen gas. Okay, 2 hydrogens to each side, we end up with the corresponding alkane. Okay, can we add just 1 equivalent of hydrogen? It depends. If we're using one of these catalysts, no. We can't stop it at just 1 addition. It's just going to keep adding. Okay, but if we choose the proper catalyst, we can do that. Okay, one of the most commonly used catalysts for this purpose is what's called the Lindlar catalyst. Okay, the problem with adding just 1 equivalent of hydrogen in this reaction is these catalysts are too efficient. Okay, we'll just keep going all the way. If we want an alkene, okay, what we can do is we can make the catalyst less efficient. Okay, so we start out with palladium metal, finely powdered, and it's added to solid calcium carbonate, okay, limestone, chalk, that has been specially modified with lead salts. And there are some other variations. Some of them use barium sulfate and a compound called quinoline, but the catalyst is partially deactivated, so it's not as efficient. Okay, when you use the Lindlar, okay, it only adds 1 equivalent of hydrogen, but the alkene that you get is exclusively cis. Okay, so this is what we call syn addition. So this only gives the cis. Okay, so we have about 5 minutes remaining. Okay, so let's take a look at some of these, starting with acetylene and with any other necessary reagents. propose a synthesis of each of the following compounds. Okay, any compound made in one part of the problem may be used in another part. Okay, so starting with acetylene. This is acetylene. And to make 1-butene, what we need to do we can use NaNH2 in liquid ammonia. And for the second step, we need 2 carbons. And a halogen. That could be chlorine, bromine, or iodine. So let's say chlorine. Okay, we would be able to accomplish it that way. Okay. Okay, how about, okay, this is part A. All right, how about part B? Okay, we want to make 1-butene. All right, this could be accomplished by taking the 1-butene that we produced in part A, and let's use hydrogen and Lindlar catalyst. Okay, that way we would only add 1 equivalent of hydrogen. Okay, although both hydrogens are added to the same side of the triple bond, this product doesn't have cis or trans stereochemistry. It's neither cis nor trans. Okay, how about 1-butanol? Okay. Okay, well, let's start with what we produced in part B. Okay, so how about if we take and this time we want to do anti-Markovnikov. Okay, so anti-Markovnikov, that would involve hydroboration oxidation. Okay, so we would use CH370, followed by hydrogen peroxide, basic solution, and that would give us the desired regioisomer. Okay, I'm going to go ahead and erase what I've got here. All right, 2-butanol. Okay, for that, we could start with 1-butene that we produced in part B. And this is Markovnikov. Okay, so rich get richer, hydrogen goes to this side, OH goes to the other side. So for this one, we could use the acid catalyzed addition of water. Okay, so for part E, okay, we want 3-hexyne. Okay, and we could start with the 1-butyne that we produced in part A. Okay, so we want to add two carbons to the other side. All right, so for this one, let's do NaNH2, liquid ammonia. Okay, that would remove this hydrogen. And we want 2 carbons and a halogen. Okay, I'll choose bromine this time. Okay, and that would give us 3-hexyne. Okay, for part F, we could reduce the product in part E with the Lindlar catalyst. Okay, and we are out of time, so I'm going to go ahead and wrap it up here. I'm going to stop the screen sharing. And I will see you on Wednesday.